Writing electronic configuration in box notation is another important method of or way of writing electronic configuration. If you want to do this, if you want to draw the electronic configuration of any element, according to this box notation, you have to know spdf notation. I don't have much to discuss about this. All what I need to tell is this. I'll explain this using one example, carbon. You know, proton number of carbon is 6. It means it also has 6 electrons. You know how to write the electronic configuration for carbon having 6 electrons in spdf notation. If anyone has forgotten, I can write 1s2, 2s2, 1s2, 2s2, and 2p2. Now, this electronic configuration in box notation is not much of a big thing. It's as simple as, but I'm going to explain to you now. Here, I'll take this part. This is the electronic configuration in spdf notation. And then I remove all these electrons from it. I don't want to show electrons. And then, you know, 1s, this is the first quantum number. To represent the 1s, I drew one box. And then we go to second quantum number. You just shift the 2s and 2p sub-energy level a little bit away to show that there's a difference. Energy level difference is there between 1s and 2s. And then you draw 2s, one box for 2s. And then next one is 2p. 2s, 2p, same quantum number. But when it comes to 2p, you know very well, it is a degenerate orbital set. P sub-energy level has 3 orbitals, right? I remember 3 orbitals. Yeah. P can have maximum 6 electrons. For maximum 6 electrons, P has to have 3 orbitals. So I write the 3 orbitals in this manner. See if you got it. All what I did was, I drew the orbitals with boxes. Now we can write 1s has how many electrons? 2 electrons. Write the 2 electrons in this manner. And there's a bit of a gap because we have quantum number difference. And then we come to 2s. You show the 2s right above the orbital. Okay. And then because it has 2 electrons, we do 2 arrows, one up, one down. And then we go to 2p. 2p has 3 orbitals. But you know the 3 orbitals, 2px, 2py, and 2pz. Why? X, Y, Z show that these p orbitals are organized in S, x orbital, y orbital, and d orbital. If anyone has a question now, I can show x orbital, x-axis, y-axis, z-axis. We have px orbital here, py orbital here, pz orbital here. Each orbital carries 2 electrons. So altogether 6 electrons. But here we have 2p2, 1 electron over here, 1 electron over here. This is the box notation for electronic configuration of carbon. It's not very difficult. I'll go to another one. This time I can talk about sodium, for example. Sodium. Sodium has 11 protons. So I know it has 11 electrons as well. If you remember the electronic configuration, I remember because I have done this very many times. 1s2, 2s2, 2p6, 3s1. We have 3 energy levels now. 3 quantum numbers are there. To draw the box notation, I can separate it from there and show down here. And see, we have 3 quantum numbers. Quantum number 1 for 1s2, quantum number 2, 2s2, 2p6, quantum number 3, 3s1. I will draw a box for this. First one, I'll draw a box for 1s. And after 1s, we have 2s. 2s is a different energy level. 2s is a different energy level. Therefore, I will leave a bit of a gap between 1s2 and 2s2. Okay, push it right a little bit. Now there you can see a gap. And then again, I have 2s2. Its orbital. Only one orbital is there. Just drop that box over there. And I go to 2p6. 2p6 means again 3 orbitals. But these 3 orbitals are to be drawn pretty much closer to 3s2, the way I did in the earlier question, because they are in the same energy level, same quantum number. Even though they are in the same quantum number, 2s and 2p are different. So you keep them closer but not attached. However, for 2p6 electrons, I draw 3 orbitals together because they are degenerate orbitals. And now we have 3s1. I'll separate 3s1 because it's another energy level. It's another energy level, another quantum number. So we had to remove that quantum number from here. So I draw it over there and then draw a box to represent the orbital 3s. And make sure to maintain a distance between the second quantum number and third quantum number, but the distance should be here lesser than the distance over there. Because when you go away from the energy level, if this is a nucleus, if this is a first quantum number, second quantum number, third quantum number, fourth quantum number, the distance between quantum numbers decreases. So the distance between first quantum number and second quantum number is greater than the distance between second quantum number and third quantum number. Let me push this 2p6 a little bit towards the middle of this degenerate orbital set. And to be very precise, I can name this p orbital set also. How? This is 2px, this is 2py, and this is 2pz. Now, I can remove the electron here. 1s2, electron can be removed, and in the box, 2 electrons can be written. And then, next one, 2s2, you remove that electron, 2s2, and add 2 electrons to the box. And 2p6, we have 6 electrons. Remove the 6 electrons from this spdf configuration and add the 6 electrons, first an electron to each orbital because it's a degenerate set, and then add the remaining electrons, 2p6. Now 3s1, only 1 electron is there. We can remove it and then 1 electron over here. This is the electronic configuration in box notation for sodium. This is electronic configuration in box notation for carbon. It's pretty simple, very, very simple. Here we have electronic configuration in box notation. This is very much similar to the spdf notation of configuration, except for the boxes drawn to represent orbitals in this method. Magnesium. Magnesium has how many electrons? It has 12 electrons. So I will write 1s first. 1s2. Up. Let me not write 2. I'll remove the 2. And then the electrons will be shown in a box. Give me a second. Yeah. 1s. This 1s is used as a label for the orbital. So draw a box. And I wrote 2 electrons earlier. Those 2 electrons are written like this. 1s. And then 1s, 2s. I leave a gap here. 2s. For the 2s also we have a box, single box, 2 electrons, 2s. And then we have 2px, 2py, 2pz. 3 boxes to represent 3 orbitals. Don't connect these 2p orbitals to 2s, but leave a gap there. And magnesium 1s2, 2s2, 2p6. 2p6 electrons. And then I think 3s2 is another energy level. So we can write 3s here. Draw box, 2 electrons. Now I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is a box notation for magnesium electronic configuration. However, now even though I drew it like this, you may not be able to do it in the first phase. So always better when it comes to magnesium, for example, write the electronic configuration for 12 electrons. One is 2, 2s2, 2p6, 3s2. First take it onto rough paper and then transfer the information into box notation. Likewise, we go to potassium. I'll write the potassium electronic configuration over here. Remember, there are 19 electrons in potassium. 1s2, 2s2, 2p6, 3s2, 3p6. You didn't go to 3D, now you can't 4s. Potassium has only 1 electron in the outermost 4s orbital. 2, 4, 10, 12, 18, 19. There are 19 electrons in potassium. First, I write 1s2, only 1s, and draw a box. 1s2 electrons are shown like this. After that, we go to 2s2, 2s. The 2 electrons are written over here, or drawn over here. After 2s, we have 2p6. 2, same quantum number, 2p6. So you draw 3 orbitals. This is 2px, 2py, 2pz. It's horrible writing over here. However, we have 6 electrons. And then 3s2. It is a new energy level now. So you leave a gap, maybe somewhere here. And this is 3s. 3s2 electrons. Afterwards, we have 3p6. So next to this, 1, 2, 3. This is 3p. 3p has 6 electrons. 1, 2, 3, 4, 5, 6. It's a bit of a mess here now. Let me remove this part completely. I'll remove this. You know how to work it out. After 3p6, we have 4s2. It's a new energy level, new quantum number. So I can write 4 as potassium has only 1 electron. And it's a new energy level. You keep an orbital here. Just 1 electron. See, we have 1 quantum number here, 2nd quantum number here, 3rd quantum number here, 4th quantum number here. Between the quantum numbers, we have maintained distances. So this is exactly how we write electronic configuration for elements in box notation. And we have 2 more electronic configurations to complete in this, argon and sulfur. But I think you can take care of it yourself. Because if I give the answers for these 2, you will not do any work. Okay, so try to work it out yourself. And with this, we are going to finish the electronic configuration of elements using box notation. This is one of the electronic configuration writing techniques out of 5 or 6. There are a few other things. We will learn them also. This is something very simple. So I hope you understood the lesson. And in other sessions, we'll see how to write electronic configuration in other ways. Okay, now I'm going to finish the session. Thank you very much for coming for the lesson.